It's a great pleasure to introduce Nikhil from BlueSpec. He's going to be telling us all the wonderful things that they're doing with our ISA. Everyone's eyes.
I got a bite. Thank you, Krista. Hi, my name is Nikhil. For those of you who are interested in details, in the part of the world where I come from, names are written backwards. So Nikhil is my first name, even though it's written last. So just call me Nikhil when talking to me. And my colleague Darius Rad is there in the white T-shirt. He's our software, hardware, and everything guru. So he knows a lot about everything about what I'm talking about as well. So I'm going to tell you about what we've been doing with RISC-V over now almost 2 years at this point. So, but I'll summarize it in one slide first and then go into more details. So basically, many of you know about the BSV language from BlueSpec and the hardware design language, but others may not know. But so just one-liner, BSV is a hardware design language that's been our main thrust of our business to date as a hardware design tool to ASIC and FPGA shops for various reasons. And we're starting to move into a new direction, which is mentioned in the first bullet here, which is basically to look at tightly coupled hardware-software accelerators for especially the more complicated the app, the better. And the more we need to move that complication into hardware for speed or energy reasons, the better, because that's the advantage of using a very high-level hardware design language on the one hand. So specifically, we are likely to be doing stuff with video and crypto, and I say that because we have discussions ongoing already with a couple of companies on those fronts. And with this focus, we're not trying to focus on the world's fastest, world's most energy efficient CPU. Really, it's more about the smooth coupling between the hardware and the software, the hardware being the accelerators, et cetera. So our in-house processors, that is, we'll, in the broad sense of things, we will be a little agnostic about what processors we use. We'll use standard interconnects like AXI and so on. But we ourselves will be providing RISC-V processors only as the in-house offering. If a customer wants to put some other processor in, that's okay. So, and we expect many of our components to be open source. So in other words, our business model is more inspired by something like Red Hat, where the product itself is open source, but the integration and the curation and the pre-testing and the support, et cetera, that's what customers pay for. So that's the kind of direction we're going. So we will have some off-the-shelf offerings, but we'll also be willing to do things custom on requests. So that's the background. I'm from BlueSpec. This is what we're moving into, and our RISC-V work is centered around this kind of activity. So today, I'm going to talk to you about some specific artifacts, et cetera, that, and some techniques we are using as we go about doing this. And we will have a poster demo later on this evening, where we will actually be, I will attempt to demo this remotely across the continent. Okay. So here's the kind of an overview of the components. And what you see on the far right is the kind of SoC structure, and all of this exists, and consisting of RISC-V CPU, an interconnect fabric, memory interfaces, DMAs, other accelerators, et cetera. We architect our things with these three interfaces, console I/O, but direct GDB interfaces, and interface for an off-board verifier for the CPU. And when we do an execution setup, it typically looks like this. We have the SoC running, maybe in simulation, maybe on FPGAs, and we connect to various things like GDB and terminals and tandem verifiers, what we call tandem verifiers. I'll say a little bit more about all of this as we go forward. We have three different things that plug into that blue box. One is called Scissor for the C instruction set simulator for RISC-V. The second is called BlueRox, and the third is called Flute. BlueRox is also just an ISS. In other words, there's no attempt to be microarchitecturally clever in any way. It's literally it reads like a C program, but it's written in BSV, but it's synthesizable therefore, and we can run BlueRox on an FPGA. So a little more detail of the 3 different implementations. For your trivia curiosity, that's how those names come about. And real trivia is this little footnote for those of you who are old enough to remember. And so in these 3 things, you can see the source languages in which the implementations are written. Flute is the pipelined implementation. Some of the features described over there. And basically, we can run the BSV things on FPGAs. And as you can imagine, when you try to boot Linux, you get about these kinds of elapsed time for booting it, depending on whether you're running it in simulation or on FPGA, et cetera. So all 3 of them are full in the sense of full integer set and floating point and supervisor mode. So they can boot the Linux kernel, they handle exceptions, MMUs, supervisor user modes, et cetera. They all have direct GDB support, about which I'll say a little bit more in a second, and they both are configurable for RB32 and RB64. So the direct GDB support is the following, which is that GDB, as I'm sure most of you know, it can be run already as a remote debugger for a remote process somewhere. And the way that works is you have GDB running locally. It runs across some connection, perhaps TCP, to your remote process. There's something called a GDB stub that sits next to the process that you're debugging, and there's something called the GDB remote serial protocol by which these 2 things communicate. All this is standard part of GDB. And typically, all of this is done just in software. And it's perfectly adequate if the rock you're standing on is stable, namely your CPU and your hardware system and your OS and so on. But as you're developing the CPU itself or the OS itself, things can get a little rocky out there. So what we've done is we've essentially created a GDB stub server in hardware, in BSV, that plugs in directly into each of those 2 BSV CPUs, BlueRox and Flute, so that you can directly run GDB using the same standard GDB and the remote service here. So that's one thing over here. Then the other thing is about tandem verification. So the way we sort of bootstrap our confidence in the correctness of these systems is we start with a C instruction set simulator, which is not formally verified, but through extensive testing of codes, we build our confidence in that. Then what we can do is, as shown in this picture, so in BSV, there is a way to import C functions directly into BSV code when running in simulation. So using that capability, we're able to incorporate that into the BlueSim simulation of BlueRox. And basically, what we do is essentially for every instruction that's retired, there's only a small piece of architectural state that's actually changed by any particular instruction. Maybe a register is written, maybe a memory location is written or read, et cetera. So those very small deltas are streamed out to this. And this guy essentially replicates the same thing. It says, I'm going to do the same instruction, and did I get the same result as you? So that's why we call it tandem verification. And we can do this, first of all, in simulation to build up confidence in BlueRox itself. But of course, it runs much slower than that because the BlueRox simulation is going to be slow. And if you're doing Flute, it's even slower because it has multiple pipeline stages that you're simulating serially. So we can take it further like that or like that. So that one is basically saying you can move either BlueRox or Flute into the FPGA, and we can stream out those deltas and run the tandem verifier on the host. And once BlueRox has enough, you have enough confidence in that, we can do that, which is run BlueRox on an FPGA next door to an FPGA version, for example, of Flute itself, so that we have very high bandwidth communication over there. So all this infrastructure is built into the architecture, the microarchitecture for these things. And the idea is that BlueRox will be the reference that we can use not only for Flute, but any other future pipeline implementation. BlueRox, in some sense, becomes our reference simulator that can be run in hardware to check other things. So a little bit more on BlueRox Flute Structure. As you saw earlier, there are these three interfaces, GDB, console, and verification. And essentially, they've been written for high reuse and adaptation and evolution. So they're all, everything you see on the slide is other than scissor, which is in C, everything else is written in BSV. And using a lot of experience we've developed on how to do this reusable stuff. And the BlueRox and Flute have exactly the same BSV interface, so they're literally drop-in replacements for each other into the rest of this infrastructure. And the other cool thing, I think, is that Flute is written in what we call a latency-insensitive style. And what I mean by that is, even though you think of these things as things on a little chip that fits on your fingernail, we still logically think of them as distributed systems. So if you think of all the stages of your pipelines as communicating agents, in classical distributed systems, you sort of try to not make assumptions about latency of delivery, for example, of messages. And you try to get a correct implementation despite variations in possible variations in latency of delivery, et cetera. We follow exactly that philosophy in Flute. That is, all the different stages of the pipelines are considered as independent processing agents, and all the connections, the usual forward data flow through the pipeline, and all the backward flows for branch redirection, for register bypassing, and everything like that is all logically treated as message passing, and whose correctness does not depend on how long it takes to deliver those messages, or even the order in which they arrive if they're coming in from different sources. So basically, this makes it very easy to replace a stage with a different implementation that may have a different latency to it, or stretch a stage into multiple stages, for example. None of those transformations has any effect on functional correctness. It can, of course, have serious effects on performance, but it doesn't have any effect on functional correctness. So the philosophy in all of these is get the functionally correct thing with all your microarchitectural algorithms, distributed algorithms like bypassing, et cetera, working correctly first, and then crank the thing to get it up to, if there's any performance issues, to fix any of those things. This is classical in BlueSpec methodology, BSV methodology, which is to think in latency incentive style and then refine it for performance. Okay, this is very speculative stuff at this point, which is exploring formal verification, which is we want to start with formal verification for Flute, and maybe shortly thereafter go into things that are just outside the core itself. And then in the future, get into things like accelerators and so on. And basically, what we're leveraging is BSV rule semantics. So this is really the key golden nugget in BSV as far as formal reasoning is concerned, and even informal reasoning from the point of view of programmers, which is that every rule has the semantics of an atomic transaction on state. So if you think of formal verification systems like PVS or TLA plus, et cetera, in all of them, you think of them as rewrites. That is, there is some concept of a state, and there's a rule which says how the state evolves over time. This semantics is exactly congruent with what you see in those formal verification systems, which is why it's very attractive for people doing formal verification. And then staying in this latency insensitive style emphasizes that. And in the past, not recently, but almost 10 years ago, in a earlier version of BSV, there's been a fair amount of work on doing correctness proofs for deeply pipelined CPU pipelines and for scalable directory-based cache coherence protocols. So we have a lot of in-house experience based on that, and we have partners who are interested in getting into all of this. So we've had some initial conversations on this, and I think we're likely to be getting into this much more this coming year. On the software front, we've made some contributions to the open source repositories, and Darius, some of these here and these here are all due to Darius out here, who's did the soft float variation on GCC and with able to run it without if you don't have atomic memory ops implemented. And another colleague of ours, Todd Snyder, did RISC-V GDB port, which is what we're using in the other slides where I showed you GDB. And that's also been put up in the open source repository. We've also adapted whatever needs to be done to get Linux kernel running on. The Linux kernel is Berkeley's release, but whatever adaptations are needed to get it to run on our stuff, we've done, that's been done. And we're not sure in terms of software sense, we're not expecting to directly focus on central software development for RISC-V. We certainly would like to go beyond just the kernel to a more full-blown operating system, but I think a lot of other people are going to be doing this, so we probably just ride on other people's shoulders for that. We've done a fair amount of RISC-V evangelism for all our shared interests, and there is a India microprocessor project that is in the offing, or at least so we've been saying for more than a year now in India, but that's how governments run. They take decisions slowly, but I think it's going to happen. And and in their early stages, literally almost 2 years ago, they were trying to decide which ISA to use. So we essentially provided a lot of information about RISC-V and contributed to their decision. And I think they have decided they're definitely going to do it with RISC-V. We're just waiting for the project to get approved and get off the ground. We also talked a lot with IIT Chennai, and maybe we played a small role in your decision also from moving from Power to RISC-V. And anyway, so we're beating the drums wherever we can. And the last slide I want to present is basically really the focus of where we're going with this. And essentially our software work and hardware work is going to be more centered around this kind of thing, which is really to make it very easy to have tightly coupled hardware software solutions to some complex algorithms. And the very high level idea is the following, which is that we'd like the user to be able to focus at this level, which is what's your application code that you're going to run on the software side, what's the code you want to run on the hardware side, and just assume they can communicate with each other easily. And what we'd like to do is from that spec of the interfaces between these two, essentially push a button and generate everything you see down here. And typically this is a stack like this. At the very lowest level, there may be some physical transport interface. We do a lot of PCIe right now. We'll also be doing things like AXI. Above that is a little more of an abstracted transport interface that's platform independent. We have something which is called BlueNoC, for BlueSpec network on a chip. And there is another set of infrastructure that comes out of Quanta research in Cambridge, Massachusetts, called Connectal. And above this, we have application-specific transactors that are generated for the particular hardware software pieces you have. And what I mean by transactors is that the communication between the software part and the hardware part are particular data types that you're trying to send back and forth, and which are completely application-specific and based on not only the data type, but characteristics of what kind of communication you want. What's important to you, is latency important, is bandwidth important, et cetera. You want to be able to directly generate libraries where the application very easily can just do library calls to send, receive, read, write, et cetera. And these guys take care of all the interfacing between that application view of things and the platform view of things over here. So this particular thing is, we've done a lot of stuff in this space over the last several years. And more recently, over the last year, Quanta Research has been doing something like this. In fact, they have a paper at the FPGA conference next month that's here in Monterey, as it happens. And their stuff is all open source. It's on GitHub. And we're exploring right now how we might want to unify these two things. And essentially, our stuff will join their stuff as open source material in the GitHub repository. So that's basically the focus of where we're going. So RISC-V for us is the enabler for this. It allows us to play around with all of this easily and adjust things wherever necessary quite easily. But really, the focus is on being able to do this kind of fast hybrid computations. And I'll stop there.
I'm Trivikram from AMD. I think you mentioned that, your last point was that your focus is on, efficient hardware-software collaboration. Have you thought of, doing something on architectural synthesis where, if I gave you a RISC-V executable and wanted you to come up with the most efficient BlueSpec representation that is formally verifiable against the ISA, is that something that you would consider, within your charter, or would you think that's outside your charter, or would you think that's science fiction at this point?
I suspect the latter, but I just want to make sure I understand your question, which is your spec is, for example, an algorithm written and compiled to RISC-V binaries or something, and you want an alternative hardware implementation or a fast implementation of RISC-V to execute that binary? What do you?
A fast implementation, which is, RISC-V.
Still a RISC-V processor,
Still a RISC-V
but it's
processor.
optimized for that particular binary.
Exactly, and that's push button, no manual intervention.
Okay, no, we have not given any thought. Just a general philosophy point, which is why just a general point I want to make regarding the term architectural synthesis and why I quickly responded that I think it's still a fantasy, which is, in my opinion, in hardware, there is no difference between algorithm and architecture, right? And in software, we take it for granted that unless you do algorithmic synthesis in the brave new world of artificial intelligence, algorithms are designed by people. You render it ultimately into software. Your software, you can optimize it. If you lost on the algorithm, you lost. And I believe absolutely the same thing in hardware. If the architectures are done by people, not by automation. Microarchitectures, second order details, fine. But top level architectures are exactly the same as algorithms in hardware. So I'll be happy to put on the boxing gloves and take that on in the breaks all this evening because, sorry?
That will be a three-way fight.
Excellent, very good.
Even B and Rodan from the EU guys, they have a formal verification environment for BlueSpec, and they seem to generate BlueSpec. I don't know how good it is.
We've occasionally had conversations with them.
Okay.
So I think Event B, TLA Plus, Unity, PVS, basically all of them have this rule-based engine underneath. And at a 10,000-foot level, they have the same kind of idea, which is it's a rule. Each rule is assumed atomic, right? So in that sense, we've certainly been attracted towards looking at that. We've tried to encourage people at, I think Southampton is the place where they did this. We haven't had the resources to do it ourselves. We kept encouraging, but I don't think anything has happened on that front.
Okay. No, we're just looking at mature tools. It's, conceptually, there's not much of an issue, but we also want to get going on practical problems.
Yeah.
So not to do research and formal methodology, but to get something up and running on BlueSpec implementation of RISC-V is my goal. So.
Yeah, no, I think also the other issue about formal verification is I have a feeling that one of the big open problems, which is why it doesn't seem to make much progress, is we don't seem to have modular ways to do formal verification, right? Which is you take a deep pipeline and everything is thrown into one bucket and everything is tried to be proved at a very low level of abstraction, right? Whereas when I think of that pipeline in the way I described as a distributed system, and with messages passing, right? I'm thinking at varying levels of abstraction. When I'm thinking of a particular stage, I need to know everything about what's in that stage. At a very high level, it's just an abstract process sending and receiving messages. That kind of modularity I haven't seen in the formal verification world yet. And if we went there, maybe we'd get further than just toy problems. Thank you.